Alrighty, in this part of our lesson on inverse functions, what we're going to do is actually go over a method to truly find the inverse. And we did that a little bit already, so we have a few examples to look at. The first couple should go kind of quick. We'll start with just a set of points. And remember the definition of an inverse. What it is it maps the domain of the original function onto the range of the original function, meaning it switches the domain and range, which really means it switches the x's and y's. So if I have a set of points, like I've got here, then its inverse is simply going to be the interchange of the x and y in each of those coordinates. So 5, 1, 2, -3, 4, 0, and -1, 2. And if you plot the original function, those 4 points, and if you plot the inverse points, if you recall, with a function graph, the graphs are a reflection over the y equals x line, and that's going to happen again with the set of coordinates. Okay, the second one. The second one we actually talked about too, and we said, you can really just decompose the function, decompose the idea that there's multiple things happening. It's a composition, and just work backwards. So we had already said the inverse of this one was x minus 5 over 2. We had done that before. But that was we were just working off intuition. So now, what about a method? Now I've got the steps right up here at the top. Whoops, got the steps highlighted here at the top. And the first thing you want to do is that f of x is definitely cumbersome to work around, so we just want to remember that it's the same as a y. And our first actual action step then would be interchanging or switching the x and y. Now what's kind of cool is the moment you do that, you're actually on the inverse relationship or the inverse equation. It's just that we don't have it in function form. So what I have numbered as step 2 up there is solve for the new y. So we've got a y on the right now, and we'll subtract 5. We get x minus 5 equals 2y. Then divide by 2, and we've got y equals x minus 5 over 2. And that's your inverse. And then what we might do is we might relabel it then as f with that inverse symbol that I don't really like too much. And so this method, what it does is, especially in more complicated functions like one we're about to see, is it allows you to do the backwards work without having to kind of riddle through it mentally without any work. Okay, let's look at these other ones here. Next one's a great example of that, how the way it is, we'll have some trouble just trying to think backwards. Not very convenient or easy at all. So let's change it to y. Some of you, on your pencil paper, you might get used to just changing it to y and switching all in one step. So now we'll do the switch. X equals 2y plus 5 over y minus 1. Now that's a little scary. We got to get that y by itself, but there's 2 of them. One's in a denominator, and I'll show you how to do that. The first thing is fractions are bad, so we want to get rid of that for solving. They're bad for solving anyway. That cancels. Now we've got everything on ground level now, but I don't like these parentheses over here, so we're going to distribute this. So we have xy minus x equals 2y plus 5. Now, how do you get multiple y's and reduce them down to one y? Well, what we do is we want to group them on the same side, the terms that have a y. So what I'm going to do is I'm going to subtract 2y over to the left. I want to get anything that doesn't have a y in it on the opposite side. So I'm going to add x to the right. Now, I'm kind of lining them up just to keep things consolidated, but if you look, these are not like terms. So I'm going to move over here to the left. We really would have xy minus 2y equals, and on the right side, 5 plus x or x plus 5. Now, I don't know if you're sure if you can see where we're going now, but we have all the y's together on the left, and we can factor one out. It'll say x minus 2 equals x plus 5, and we're there because we divide by x minus 2. So now we've got the inverse. The y, or now the f inverse of x, is equal to x plus 5 over x minus 2. A little more work on that one, and it's certainly not one that you're going to just look at and be able to, think through it backwards. So, last one is a square root one, and we talked a little about squares and square roots. So this is a quick one to run through the algebra. We got y equals square root of x minus 2. Switch them. X equals square root of y minus 2. Get the y by itself, so let's square both sides. So we have x squared equals y minus 2, because the square cancels the square root. And add 2, and boom, we've got our inverse function is equal to x squared plus 2. But there's a problem here. The domain of the original, we can only plug in x is greater than or equal to 2, or else we'd have the square root of a negative. So when we do our interchanging, we have to think through what's the domain of this original one. So if I plug, what we want to think about is if I plug 2 into this, what do I get? 2 minus 2 is 0, and the square root of 0 is 0. So the first range value is a 0. That means for this one, the first domain value would be a 0. So we want to put that restriction on the domain here. Domain is greater than or equal to 0. We'll take a quick peek at Desmos for that, so we can look at the graph. Got all our old ones in here from before. Let's clear them out. And what I'm going to do is, again, I'm going to employ a fraction exponent here. So we have x minus 2. Let's delete out this old stuff. To the 0.5 power. And whoops, I have it turned off. There it is. So then if we do our inverse, which is f of x equals, you don't need inverse notation when you're using the grapher, x squared plus 2. You can see the reflection, okay, but we only want to look at the correct half of that. So if you remember in here, it's kind of funny, we use set notation, put in our restrictor. For the visual on it, you really just need greater. You don't need greater than or equal to. And then a comma. And oops. I'm sorry. Oh my goodness. A bunch of equals here. I'm sorry. It's a colon. Colon x squared. And then plus 2. And so now we've restricted it just for the x is greater than 0, and we see that reflection. Okay, one more quick note, verifying inverses. And one way you can do that is this composition must be true. F of g of x equals x, and g of f of x equals x. So we're going to use the one that we found, a little bit, one of the simpler ones. We got the 2x plus 5, and then we had its inverse. I'll just use g for now for that. This was x minus 5 over 2. And what this is saying is, if you take the entire function, replace it for x, what should happen is everything should cancel and it should reduce to an x. So let's do that. So if we take f and we plug g of x into it, it would be 2 times x minus 5 over 2 plus 5. Well, watch, 2's cancel. We have x minus 5 plus 5. The 5's cancel and we have an x. That's very compelling. That it's an inverse. It should work both ways. So if we take the 2x plus 5, replace it for the x here, that means we're taking the g function, we're plugging f of x into it. And so we'd have 2x plus 5 minus 5 over 2. Well, 5 minus 5 is 0. Then we have 2x over 2. The 2's cancel, and we have x. When that happens and reduces down, that's your way to verify for sure that one function's the inverse of another.